Chapter 4, Part 2, Cis-Trans Isomerism and the EZ system. So we've seen the term cis-trans isomerism recently when we were looking at cyclohexanes. The definition of cis and trans is staying the exact same. It's just kind of how we're analyzing it that might feel a little different. But cis still means that you have substituents on the same side, only this time we're talking about being on the same side of the alkene. So if this is the plane of our alkene, these two substituents are on the same side of that alkene. And that's especially clear when you look at the line bond drawing. So this molecule is called cis-2-butene. This other version is trans, and trans means the substituents are on opposite sides of the alkene. So if our alkene is right here, then the methyl group here and the methyl group here are on opposite sides. And again, it's even more clear when you see it in the line bond drawing where the hydrogens are omitted. So cis-2-butene and trans-2-butene are different molecules, even though they look very similar, and they are not interchangeable. It kind of seems like when you look at these that maybe there's some sort of chemistry that could be done that would allow these to go back and forth. And there is chemistry that you can do that can change an alkene from cis to trans, but it's not like a resonance form. So these are not the same molecule. They have to actually undergo a chemical change in order to change into something else. So let's look at how cis and trans is used in nomenclature. You may have noticed that in our previous chapter, the only alkenes that we named started with the number 1. They were all at the beginning of the chain. And that's because once they move into the chain, you do have to start indicating cis and trans. So when there's only one substituent on each carbon of the alkene, you can use cis and trans to indicate which isomer you are naming. So here are two examples of that. So let's follow the same rules that we laid out before. This is carbon 1 because it's closest to the alkene, carbon 2, 3, 4, and 5. We have a methyl group on carbon number 4. So it can feel kind of overwhelming at first when you realize, oh no, I have to add in cis and trans and all this other stuff. But go ahead and name the alkene the same way that you would normally. So the name of this molecule is 4-methyl-2-pentene. Right, we have a methyl group on carbon number 4. We have 5 total carbons. My alkene is on carbon number 2. So that's where all the pieces of my name came from. Now, if I look at this, the methyl and this isopropyl group are on the same side of the alkene. So that makes this the cis isomer of this molecule. And if we look at our other molecule on the page, we need to start numbering down here. And these are actually the same molecule. Well, the same alkene, but different isomers. So we have a methyl on carbon number 4, we have our alkene on carbon number 2, and we have 5 total carbons. So this is also 4-methyl-2-pentene, but this time the substituents are on opposite sides of the alkene. So that makes this the trans isomer. Trans, and there's a little dash there too. Now, there are times that cis and trans doesn't work, and that is when there's more than one substituent on one or both of the sp2 carbon atoms, because cis and trans relies on saying the only substituents that are on this alkene are either on the same side or they're on the opposite side. And if you have too many substituents, you can no longer just make that association. So you have to look at all these substituents on the carbon, and then we end up prioritizing them. On the next slide, we'll talk about how those priorities work. But once you've gone through the priority process, if your two higher priority items end up being cis to each other on the same side, we call it Z. Z stands for the German word zusammen, which means together. My organic professor would make kind of a lame joke, but it stuck in my head. a good, I guess it's been like 17 years. So 17 years later, this is still how I remember this. He would say that the substituents were on the same side of the alkene. And then if you find that your high priority items are on either side of the alkene, then we call it E, which stands for entgegen, which means opposite. And again, I already said the joke out loud, but either side is going to get the determination E. So Z goes with cis. The high priorities are cis to each other. And then E goes with trans. The high priority items are trans to each other. So there's an example up here in the corner of what a situation where cis and trans doesn't work might look like. So the reason you can't use cis and trans for a molecule like this is that this methyl group is the only thing on this carbon, right? And it is cis to the methyl, but it's trans to the isopropyl group. So what would you call this? Cis-trans? By using both words, you're kind of negating the purpose, and it doesn't say what is cis to what and what is trans to what. So using the E and Z system makes it very clear because you first assign a priority, and then you say my high priority items are cis or trans to each other. So we are going to go through the process of making these priorities, and it is kind of tricky, but this process that we use is called the Kahn-Ingold pre-log system. And we actually use the Kahn-Ingold pre-log system multiple times in this course. So we're going to use it now, and we're going to use it again in chapter 6. And then you'll use both of these skills a couple more times throughout the semester. So this is something that, even though it takes a little bit of practice, it does get used often enough to justify the practice, in my opinion. So you use the Kahn-Ingold pre-log system to determine the relative priorities of the substituent on the alkene carbons. And the Kahn-Ingold pre-log system goes by atomic weight. So the higher the atomic weight of an atom, the higher the priority. The part that's tricky is that you move out from your alkene carbons one atom at a time until a point of difference is found. Now, those words sound simple enough, but the idea is kind of tricky to explain without just working through an example. So I've provided 4 examples here on this page and then several more on the following page. So I started us off with some really easy options. And easy. But to be clear, there are times when you can use cis and trans and also still apply EZ. EZ can always be used. Cis and trans can only be used in situations like these 2 molecules. Whoops, I'm using white and you cannot see that. Only these 2 molecules on this page could be named using cis and trans, but all 4 of these could be named using E and Z. So when in doubt, use E and Z. So we're going to use the E and Z process to figure out whether this one is E or Z, even though I recognize that it's already quite clear that it's Z. But let's prove it. So the first thing you have to do is fill in any blanks that you have. So in this case, that's hydrogen atoms. The next thing you have to do is either draw an actual line or draw a mental line. And we are going to be analyzing each of the carbon atoms of the alkene separately. So first, let's look at this left-hand side. On the left-hand side, we look at the 2 items that are attached to the carbon, and we decide which one is the higher priority. Since this is done by atomic weight, the chlorine is the higher priority. Then we look at the other carbon, and we look at the 2 things attached to that carbon, and we decide which ones are the higher priority. And that's going to be the chlorine. So once you've decided your high priorities, you then look at the alkene and decide, are my substituents cis or trans across my alkene? These substituents are cis, they're on the same side. So this is a Z isomer. But also cis because it's only 2 substituents. So for the next one, we're going to do the same process. So we analyze each carbon independently, and since we already did those exact priorities, I'm going to do this a little quicker. Chlorine and chlorine are going to be our high priorities. So then once you've decided those priorities, you look at the alkene and decide, are my chlorines on the same side of the alkene or opposite sides? And they are on opposite sides. So that makes this E for either side. And this is also the letter that goes with trans. So that's how you do it in these very simple situations. So let's make it a little more complicated. On this next molecule, we have 2 carbon atoms, right, in the alkene, and they have different substituents on them this time. So the first thing we need to do is look at our carbon on the left and compare chlorine and bromine and decide which one is the higher priority. If you look at the periodic table, you'll see that bromine is below chlorine. So this is a bigger atom, higher atomic weight equals higher priority. And then on the next carbon of the alkene, we have chlorine versus hydrogen again. We know that chlorine is bigger than hydrogen. And then we look at our alkene and say, okay, are my substituents of high priority on the same side or either side? This is an either side situation. Now, I'm not going to write the word trans this time because I could not use trans to name this even if I wanted to, because the bromine is trans to the chlorine, but the chlorines are cis to each other, right? So it doesn't give a full explanation of what this is. Okay, so this next one is where we're going to understand this second rule. Move out one atom at a time until a point of difference is found. So what I found works for my students is to color code extraordinarily heavily while working through this. So we're going to analyze each carbon of the double bond independently. And it says move out one atom at a time until a point of difference is found. So that means that we're going to do our priority comparisons in layers. So in my first layer, my left-hand carbon, let's call it carbon A, and we'll call this one carbon B just to make our discussion a little easier. Carbon A is attached to a carbon atom and a carbon atom. According to the system, even though it's very, very clear to us that ethyl is ultimately going to end up being larger than methyl, we don't want to make that assumption, and I'll show you an example on the next page that proves why. So at this point, we are comparing 2 carbon atoms, and we do not make a decision at this point. We go to the next level. So what are we comparing at the next level? Well, this top carbon is bonded to a hydrogen, and another carbon atom. The bottom carbon is bonded to a hydrogen, and a hydrogen. So now we're comparing carbon, hydrogen, hydrogen to hydrogen, hydrogen, hydrogen. Carbon, hydrogen, hydrogen is going to be the higher priority. So the ethyl group is the higher priority because we get to another carbon, whereas on the lower one, we don't have any more carbons, we just have hydrogens. So the top group is the priority because of that. Now on carbon B, it can be tempting to say, okay, I'm comparing hydrogen to isopropyl. Obviously, isopropyl is larger, but that's not what the system says. The system says that we are comparing hydrogen to carbon, and carbon is bigger than hydrogen, so we're going to choose the isopropyl group. So when we're done picking our priorities, we see that our priorities are on opposite sides of the alkene, so this is an E isomer. Okay, so hopefully you're following along, but if you're not, you're in luck. There's more practice problems. I'm going to work through some of these a little more quickly. So I'm no longer going to draw the vertical line every time that I do this. I want you to start to be able to do this a little more quickly. So we have, here are carbons of the alkene. I need to compare this group to this group. Now we just did this exact comparison or something very similar, so I'm not going to make us go through it again right now. This is going to be our high priority. And then on our second carbon, we're comparing methyl to hydrogen. So methyl is going to be the high priority. This has our two substituents on opposite sides. So this is E. If you would like to practice on your own, please go ahead and pause. And then if you get stuck, you can unpause the video and try to catch up to where you are. Okay, let's go to the next one. This one's a little more tricky. I will draw the line just because I drew the alkene at an angle. So we are comparing the carbon on the left to the carbon, or sorry, we have to do the priorities on each of the carbons, the one on the left and the one on the right. Let's go ahead and do carbon A and B again. So on carbon A, we have a bromine being compared to a carbon. Now, even though this overall group is larger than the bromine, this top substituent gets us to bromine faster. So that ends up being the priority. This bromine beats out this carbon atom that I drew in here. So that's one of the reasons that you have to use the Kohn-Ingold pre-log system and not to say, oh, I know this is bigger. Because yes, you're not wrong, but the bromine is more important than the carbon. And the reason that they do this is because what if this were all attached in a ring of some sort? Then at what point around the ring do you stop? You go out one atom at a time so that the moment you get to something different, you can make a decision. So for carbon A, the priority is just the bromine on its own. Now going to carbon B, we have a methyl group versus a hydroxyl group. Again, methyl overall is heavier than hydroxyl, but we're not comparing methyl to hydroxyl. We're comparing carbon to oxygen, and oxygen is more important. So the oxygen gets the priority. Actually, I misspoke. I think they would have the same weight because oxygen weighs 2 more atomic mass units than carbon, and the methyl group has 2 hydrogens. So I think overall their weight would be approximately the same. So the hydroxyl group ends up being the priority because the oxygen is bigger than the carbon. So these priority groups are on opposite sides. This is an E isomer. Now, looking at the instructions, it says to label each of the compounds below as E, Z, or neither. Neither is an option, but you can also supply cis or trans in addition to E or Z. I wanted to throw that out there because there are examples on here where we can use cis and trans in addition to E and Z. So let's do this next one. We can do this pretty quickly. So looking at each of the carbons of the alkene, we can see that we have hydrogens here. It's pretty clear that our priorities are here and here. And this is a cis isomer. So this is going to be Z, and you can also say cis. Okay. Now let's get to this example down here. If we want to draw our line through here, we can. We are comparing this carbon on the left and the carbon on the right, the priorities on those. So starting with the carbon on the left, we have a methyl versus a methyl. This is the first example of a neither answer. This is neither E nor Z, and it's not cis or trans either. Since we cannot make a decision between the methyls because they are identical, that means that giving this identification just doesn't matter. E and Z indicates that we are locked into this certain isomer, and if we were to flip-flop any two of our substituents, we would end up with a different isomer. If we were to flip-flop these methyl groups, we would still have the same molecule, same isomer. So it's not important whether this is E or Z, and they cannot be decided as E or Z anyway. So this is neither. Okay, going to our next one. We have our alkene like this. We have our high priorities like that. So this is going to be E and also trans because there's only 2 substituents on here total. There's 1 on each carbon, so we can use cis or trans. Okay, last one. This is a fun one as far as comparing carbons goes. So here are our 2 different alkene carbons. We can do the one on the right really quickly. It's pretty clear that the carbon is going to beat the hydrogen. Let's do our layers on this next one. So we are comparing carbon to carbon. We do not make a decision at this layer because we can't look at two carbons and say, one of those is more important than the other. So we go out to the next layer. This top carbon is attached to a carbon and two hydrogens. This bottom carbon is attached to 3 carbons. So this one is going to be the high priority because we have those 3 carbons. Even though this one overall, 1, 2, 3, 4, 5, yeah, actually has more carbons and does weigh more altogether, it's the bottom one that's going to be given the higher priority using the Cahn-Ingold-Prelog system. So then we look at our alkene, and our high priorities are on the same side of the alkene. So this is an example of a Z isomer. And that is the EZ system and how it works and sometimes doesn't work with cis-trans.